Every time you open a shopping app or streaming service, an algorithm analyzes your behavioral history. The goal of this system, known as consume intelligence, is entirely mathematical. Calculate your preferences to maximize conversion and retention. This works in traditional markets because of buyer-seller symmetry. Your functional need or personal desire aligns cleanly with the market's supply. You want a specific item, the seller wants you to buy it, and the algorithm connects the two with minimal friction. When these exact commercial architectures are deployed in educational systems, the mechanism fails. Educational consumption operates on entirely different dimensions. It is epistemic, meaning the user is acquiring objective truth. It is developmental, requiring the active building of cognition and skill. And it is temporal, carrying long-term impacts on a user's future capabilities. A system cannot serve these dimensions while optimizing for a quick transaction. The algorithm must abandon product fit and optimize instead for learning fit. The variables that dictate learning fit are rigid. Factual correctness must override a user's existing preferences, and an appropriate level of cognitive difficulty must take precedence over user comfort. Applying a commercial recommendation algorithm to an epistemic domain forces a choice between user satisfaction and the rigorous requirements of long-term formation. To see how that choice changes the nature of the education, we have to analyze the physics of the learning process itself. The brain kinematics model illustrates learning as a strain-matching interaction between the learner and the content. Optimal learning, or resonance, is the precise mathematical alignment where the material's challenge perfectly matches the user's comprehension. If the material is too easy, it creates understrain, resulting in cognitive boredom. If too difficult, the system creates overstrain. The structure breaks down entirely, resulting in confusion and immediate disengagement. To maintain that narrow band of resonance, a true learning fit relies on demand-side variables, level appropriateness, clarity of explanation, and the management of cognitive load. Because the goal is accurate knowledge acquisition, factual correctness must mathematically outweigh user preference. A system that shows you only what you want to see cannot teach you what you do not yet know. Educational technology platforms frequently fall into a predictable engineering trap. To drive their engagement metrics, they design user interfaces that artificially reduce search strain by feeding learners frictionless, easy recommendations. This frictionless design successfully mimics the high engagement state of understrain. The user feels they are rapidly consuming knowledge, but no actual cognitive development takes place. This graph charts the hidden strain risk paradox. As visible effort approaches zero, the hidden strain on cognitive processing spikes sharply upward. Lowering effort does not equate to higher learning. That invisible strain manifests in three ways: exposure to unchecked misinformation, intellectual dependency on the algorithm, and the shallowing of complex topics into bite-sized entertainment. The platform has simply shifted the burden. The user no longer expends effort deciding what to learn, but they pay for that convenience through long-term diminished capability. Engineering an educational platform purely for frictionless engagement actively degrades a user's cognitive development. It replaces visible effort with invisible harm. We can track the long-term effects of this degradation using continuity theory. This animated timeline maps learning as continuous movement forward toward a state of cognitive balance.
In this model, an AI recommendation is not a passive suggestion. It is an active force vector physically altering the learner's trajectory along the timeline. A stable path requires constraints to keep the learner moving forward effectively. Stability is achieved through gradual strain increase, iterative correction loops, and multi-source validation. The vectors guide the user, anchored to the balance axis. Engagement-driven recommendation vectors strip away constraints, forcing an immediate transition to an unstable path. Without verification, the system pushes high-amplitude content for emotional engagement, knocking the learner off the axis of understanding. The root cause of this instability is the dual optimization problem, the inherent tension between the platform's supply-side metrics and the learner's demand-side requirements. The supply side seeks to optimize profit, user engagement, and retention. The demand side requires actual learning, deep understanding, and eventual mastery of the material. Unchecked commercial AI inherently favors the supply side. It is mathematically easier to optimize for human attention than it is to parse out and painstakingly verify objective truth. The resulting system generates high rates of content consumption, but critically low rates of actual learning. Unless an AI vector is mathematically constrained to prioritize demand-side mastery, its success is measured only by the user's continued attention. This indifference to accuracy turns the system into an engine for misinformation, destabilizing the learner's path. Systems designers must recognize a strict boundary. Artificial intelligence cannot mathematically or ethically function as a pure information seller in an epistemic market. This educational consume intelligence matrix maps the required architectural changes. Optimization must shift from engagement to mastery. Broad behavioral profiling is replaced by minimized cognitive tracking. Finally, the AI's identity transitions from a persuasive sales agent to a non-manipulative guide. Under these constraints, the AI takes on 4 bounded roles. First is the curator, filtering resources from the noise. Second is the translator, adapting complex material to the learner. Third is the tutor, providing structured feedback and practice. Fourth is the navigator, reducing search space to prevent fatigue, without eliminating the necessary cognitive challenge required for resonance. These constrained roles directly satisfy major regulatory anchors, aligning the platform with FTC fairness mandates against manipulation and GDPR requirements for strict data minimization. For EdTech engineers moving forward, the primary design principle is structural separation. The recommendation engine must be entirely decoupled from the platform's profit incentives. To build epistemic trust, user interfaces must evolve. Platforms must present explicit source transparency and visible confidence levels alongside any AI-generated response. The platform must also enable active user control, providing learners with clear pathways to correct the system's assumptions and override its recommendations. Covert manipulation is prohibited. The algorithm cannot be permitted to quietly bias its educational recommendations toward higher-margin course offerings or internal upsells. When these constraints are implemented, consume intelligence evolves into learning intelligence. These new systems shift their focus toward verifiable developmental outcomes rather than maintaining a high volume of transactions. Ethical platforms must be deliberately engineered to minimize both visible decision strain and hidden epistemic strain. In the physics of education, truth must always outrank engagement.